Hello and welcome back to our special series on logarithms. This unit we will learn about properties of logarithms and using the properties to expand and condense logarithmic expressions. We will then dive into several ways to solve logarithmic equations. So get your pencil and paper ready because it's time to learn about math. Before we get into new information, let's quickly review what we learned in our previous video. A logarithm is most simply described as another way to write an exponent. For the purposes of this course, logarithms help us solve for variables that are exponents in equations. In this example, 2 to the x equals 5 can be rewritten as log base 2 of 5 equals x. There are some special logarithm values that greatly increase the usefulness of logarithms. A logarithm with any base greater than 1 of 1 will equal 0 because that same base to the 0 power will always equal 1. Log base 4 of 1 will equal 0 because the exponential form 4 to the 0 power equals 1. Also, the logarithm of a number with the same base will equal 1 because any non-zero number to the first power will equal itself. Log base 7 of 7 will equal 1 because 7 to the first power equals 7. A logarithm with the base of 10 is called a common logarithm. If no number is written in for the base of a logarithm, then the base is assumed to be 10. Log of 100 really means log base 10 of 100, and that has a value of 2 because 10 squared is 100. A logarithm with the base of e, also known as Euler's number, is called a natural log and abbreviated as ln. In this example, we have e to the x equals 14, and that could be rewritten as a logarithm log base e of 14 equals x. Now, we just learned that log base e is actual natural log, so that can be rewritten as the natural log of 14, or ln of 14. And using a calculator, the ln of 14 is approximately 2.639. This means e to the 2.639 power is approximately 14. Let's take a look at the inverse properties of logarithms in exponential equations. So log base b of b to the x will equal x. And you'll remember log base b of b, this whole part right here, is just 1, because any number to a certain power that equals itself, that exponent has to be 1. So that's 1. This x right here, though, we're going to move that in front. That's actually called the power property, and we'll get to that soon. But x times 1 is just x, and that's where that comes from. So in an example using numbers, log base 3 of 3, this whole part right here will all be reduced to 1. So that reduces to 1. The 5 will come down in front. 5 times 1 is 5. Now the same thing can be true for exponential equations. If you have log base b of x and you raise it to the power of b, so b to the power of log base b, this right here, that whole thing just equals 1. And you'll notice that this x right now is written as an exponent, so power property, we'll put it in front, x times 1 equals x. Or 3 to the power of log base 3, notice the base and then the base of the exponent are the same number, that all reduces to 1. And this 6 will come down in front, and it will just equal 6. 6 times 1 equals 6. So simplifying the expression, log base 3 of 3 to the second power, so this 2 is an exponent on a logarithm, we'll move it in front, it just becomes 2 times 1, which equals 2. And then 3 to the power log base 3 of 12, well, this part of the logarithm will also serve as an exponent, so it will come down in front, and the 3 to the log of 3 becomes a 1, so 12 times 1 will equal 12. This inverse property of logarithms is a major way in which we solve equations with logarithms. We will do many, many more examples coming up in this video. The change of base formula is the most convenient way to solve logarithms that do not have integer solutions. Now, using the one-to-one property is great if our solution is going to be an integer solution or even an easy rational solution. But in our example, like log base 4 of 12, there's no power of 4 and no simple power of 4 that will equal 12. So we know we are going to have an irrational solution, and the best way to find those is using the change of base formula. Now, to use the change of base formula, we could take a number like log base b of a and rewrite it as a fraction log base c of a over log base c of b. So it might look at first that we're making it more complicated by adding an additional base into our logarithms and making one logarithm into two. But the c there, we're going to use two of the more common logarithms. So for example, we use the common logarithm. We'll use a base of 10. So instead of log base b of a, you can write log a over log b. Remember, that's log base 10 of a over log base 10 of b. And since the numerator and the denominator have the same base, we are using the change of base formula. That base just happens to be 10, and we can write it really simply without writing the 10 in there. And we have calculators that have log buttons on them, so we can use log a divided by log b in order to solve an equation. Likewise, instead of using log base 10, we could use log base e, or natural log. So log base b of a equals ln of a over ln of b, or the natural log of a over the natural log of b. And this will work equally as well as using just straight log, the common logarithm, but you get to choose which one you want to use. So log base 4 of 12, we can solve this by rewriting it using either regular common logarithm log or natural log, and I will use natural log. So log base 4 of 12 is the same thing as saying ln of 12 over ln of 4. Now, calculators are sophisticated enough to be able to write this all in at one time, to write ln of 12 divided by ln of 4 all at one time. And that is preferable because you will have the least amount of error in rounding. It is possible to find the value of the ln of 12 and then find the value of the ln of 4 and then divide the two and find an answer, but you're rounding two times before you're finding your actual solution, whereas if you put it all in at once, the calculator rounds it to 9 decimal places either way. So the ln of 12 divided by the ln of 4 is 1.792, and I'm actually going to delete that equal sign and rewrite an n as approximately, because that is an irrational number, and I'm not going to write equals when I really am writing an irrational number after it. So 1.792, what does this mean? This means that 4 to the 1.792 power is approximately equal to 12. And that makes sense because 4 squared is 16, and 4 to the first power is 4, and 12 is certainly a lot closer to 16. So it actually makes sense that 1.792 is approximately 12. All right, let's move into some of the newer things that we are going to learn. Okay, so now let's look at the properties of logarithms. And some of these words on this page you might have seen before because they are the same properties as exponents. And that should really make sense to you because exponents and logarithms are kind of the same thing. Logarithms are just a different way to write an exponent. So we have to make sure that all of our bases are a number that does not equal 1 and that m and n have to be positive real numbers in these in order for them to work. All right, so the product property, log base b of mn equals log base b of m plus log base b of n. And let's see that with numbers. So log of 2 to the 3x equals log base 2 of 3 plus log base 2 of x. Now, this actually should make a little bit of sense because the product property of exponents says that like x squared times x to the third is actually x to the 2 plus 3, and that's x to the fifth. So with exponents, when we were multiplying them together, really ended up adding those exponent values together, and that is what's happening here. It's log base 2 of 3x equals log base 2 of 3 plus log base 2 of x. So we split up the part that's being multiplied and then added as two separate logarithms. All right, the quotient property. Once again, let's do one out that has exponents. So x to the third over x squared ended up being x to the 3 minus 2, which is x to the first power. That was the quotient property as it applied to exponents. Let's see how it applies to logarithms. Log base b of m divided by n equals log base b of m minus log base b of n. So you have one logarithm here and two numbers being divided. That can be rewritten as two different logarithms being subtracted, just like our division problem turned into a subtraction problem here. So using numbers, log base 3 of 13 divided by 4 is the same as saying log base 3 of 13 minus log base 3 of 4. And the power property is actually something we talked about in the last video, and we've already talked about before to this video. Notice we have a logarithm here, log base b of m to the n power. There's an exponent of this number, and that exponent can be written around and in front right here, n times the log base b of m. So if you have an exponent as part of the logarithm, you can switch that out and just write it in front of the word log. And let's see how that works out with actual numbers. Log base 4 of 5 to the third. This 3 being an exponent can be written in front 3 times, that means times, log base 4 of 5. So the exponent actually becomes multiplied in front of the log base 4 and 5. Okay, let's use these properties of logarithms to expand a couple of logarithms. Okay, here we have a log base 3 of 7x to the fourth y. Now, all of this is part of the result of the logarithm. So log base 3 of 7 times x to the fourth times y. We have a lot of things being multiplied by each other. So I know because they're being multiplied, I can rewrite this as three separate logarithms. One would be log base 3 of 7. And all of these logarithms I write out will have the same base of 3. So log base 3 of 7 plus log base 3 of x to the fourth plus log base 3 of y. So we expanded out this condensed logarithm, which had three numbers being multiplied by each other, and we wrote it as three separate logarithms. But there's actually one more thing that we can deal with here. We have an exponent of 4 here, and so I can bring that down and write it in front of that logarithm. So I will do that. Let me say that's equal, and this is equal to log base 3 of 7 plus 4 times log base 3 of x plus log base 3 of y. All right, that's pretty cool. Now let's move on to the natural log problem. This has a whole bunch of fun in it, doesn't it? This might take a while. So ln of, and then the fraction inside parentheses, 3x minus 2, all of that being squared over 4. So we have a division part, so we know we're going to have some part here that is being subtracted because division turns into subtraction. We have an exponent, and that will be written in front. And we also have 3x minus 2, which is like a whole expression, and we can't really actually break that apart. So that will be part of the ln, and we'll keep that all together, but we'll write the 2 in front. So let's do that now. 2 times the ln of 3x minus 2, and any number written in the numerator will be like positive. The coefficient will be positive. In this case, it's a positive 2. But we will subtract from that or make the coefficient negative for anything that's being divided or finds itself in the denominator. So minus ln of 4. And it would be nice if I could split up the 3x minus 2, but I can't. There's a subtraction part in there. If it was just 3x, I could split it up. Or if there was something I could factor out, I could split that out. But 3x minus 2 is not factorable. Okay, so that's as simple as we can make that, or as expanded as we can make that, actually. Simplifying usually means condensing. Okay, we tried expanding logarithmic expressions. Now let's condense some. So I see log base 4 of x minus log base 4 of y. And the first thing I have to look at is to make sure that my bases are the same. I can't condense anything that has different bases. So if they were different, I'd have to rewrite the logarithm so they were the same, or I would just leave them as is because they might be as simple as possible. But here we have log base 4 of x and log base 4 of y, and that's wonderful because they are the same bases. There's a subtraction sign in front of it. There are no numbers in front of the word logs, which means I don't have any exponents to deal with here. The x doesn't have a negative coefficient at all, but there's a minus sign in front of the log base 4 of y. So that means y will be in my denominator, and I will rewrite this with a single logarithm. So log base 4, and x will be on my numerator, and y will be in my denominator. Log base 4 of x over y, you can put in parentheses if you want, you don't need to. But that is the condensed version written with just one logarithm of log base 4 of x minus log base 4 of y. So you can see we're going backwards from the expanding. Okay, 2 ln of 8 plus 5 ln of x minus 4. So we have a plus here, so we're going to make this a multiplication. They're both ln, so they both have the same base e. There's a number in front of that and a number in front of this, so we have exponents for each of these. So I can rewrite this as a single natural log. They're being added, so I can multiply them. So it is 8 squared, ln of 8 squared, times x minus 4 to the 5th. And I certainly can, multiply out 8 squared. That would be the ln of 64 times x minus 4 to the 5th. And I could also multiply out x minus 4, but that will give me a giant number. So I'll just leave it like that. Okay, let's take another look at the one-to-one property. This actually appeared in our last video, but this is one of the major ways that we are going to solve equations with logarithms in them, is using the one-to-one property. So if two numbers equal each other and they have exactly the same bases, a, in both of these cases, even if their exponents are different, I know that their exponents will equal each other. So a to the x equals a to the y if and only if x equals y. So whenever you see two numbers with the same bases and their exponents might be different, those exponents, as long as there's an equal sign in between them, those exponents actually do equal each other. This also works with logarithmic equations like log base a of x equals log base a of y. Well, the log base a is the same on both sides, and there's an equal sign. That means x must equal y. And you can see that here. So let's look at some problems that use the one-to-one property. Okay, we have 2 to the x equals 16. And right now, I could rewrite this as a logarithm and try to solve it that way, but I'm going to use the one-to-one property, just like the directions say. So I need to rewrite 16 as a number that has a base of 2. So 2 to the x will stay for now, and that will equal, I need my bases to be the same, 2, and 2 to the 4th is 16. So this means that x equals 4. And that's how we solve that. Okay, in the next problem, we have ln of x minus ln of 4 equals 0. This is weird because they're both on the same side of the equal sign, and we haven't seen that before. But you know what? We're going to add ln of 4 to both sides. So add the natural log of 4 to both sides, and anything plus 0 is itself. So ln of x will equal ln of 4. Now, since natural log is just log base e, it has all the same rules and the same one-to-one property as log has, the ln of x equals the ln 4 is essentially saying x equals 4. And I know the first and second problems have the same solution, but they are discrete problems. Now, in the third equation here, we have 1/3 to the x equals 9. And this is a little weird, right? 1/3, well, 9, I could rewrite 9 as 3 squared. That's fine. But 1/3 is not the same thing as 3, but it is 3 to the negative 1 power. So let me rewrite this. 1/3 to the x, I am going to write as 3 to the negative 1 times x power. And that equals 9, which is 3 squared. So negative x equals 2, which means that x equals negative 2. Now, using inverse properties is the second most common way that we are going to solve equations that have logarithms in them, or even exponential functions will be solved using inverse properties. So let's quickly review this. Look, a to the power of log base a of x. So we have an exponent, and in the exponent is a logarithm itself. But notice, the base of the exponent and the base of the logarithm are the same. That means this whole thing will just be 1. This x over here, well, that's an exponent all kind of by itself. We're going to move it in front, and it will just make the entire thing equal x. So a to the power of log base a of x equals x. Another thing is, if we have a to the x and we have log base a in front, log base a of a, that whole thing is 1. This is an exponent power property. Drag it in front, it just equals x. So log base a of a to the x power equals x. These make a little bit more sense when you see them in a problem. Okay, here we have e to the x equals 5. And one thing you can do with this is just rewrite it as a logarithm, or in this case a natural log because it's base e. But another thing you could do is rewrite this as multiplying both sides by ln. So ln of e to the x equals ln of 5. And this is using the inverse property because what's the opposite of e? ln. So ln times e will cancel the ln and e out. And the x that was an exponent now will come down in front. So x will equal the ln of 5. But you might be like, whoa, what's the ln of 5? Well, whenever e is involved, you usually have an irrational number. So the ln of 5 is approximately 1.609. So e to the 1.609 power is approximately 5. If we go to enough decimal places, maybe we'd say equal, as long as it fit within our specification there. All right, let's move on to the next one. ln of x equals negative 2. Well, what's the opposite of the ln? What's the inverse of ln? And that's e, or e to the x. So we are going to raise both sides of this equation to be powers of e. So what will that look like? E, and then the exponent will be ln x, because that's what's on the left side of the equal sign, equals e to the negative 2 power. Now, over here we have e to the ln, and those are inverse properties. Those are inverse functions, so they will eliminate each other and become a 1. We do have the x, which we'll rewrite down in front here. So let's do that. This rewrites into x equals e to the negative 2. And remember, e, Euler's number, is 2.71, but it's irrational. It keeps going. So I will use my calculator for that. Most calculators have an actual e button on the calculator themselves. So e to the negative 2 power is approximately 0.1 0.135. So the ln of 0.135 is approximately -2. Okay, let's move on to the last one. Log of x equals -2. Okay, so we are going to use an inverse property. So the opposite of log is, well, remember this is log base 10, right? So if we raise log of x to the power of 10, let's write that out. Let's see what that looks like. 10, and then make log of x the exponent. Log x equals 10. You know, we do on the left side of the equation, we have to do on the right side, to the -2 power. Now this one's great because it has an integer answer. 10 to the -2 power, well, 10 squared is 100, but 10 to the -2 power will be 1 over 100. And on the other side of our equation, remember this part right here, the 10 and the log, those reduce to 1, and then the x will come down in front. So 1 over 100 equals x. Or x equals 1 over 100. Symmetric property. All right. That was thrilling. Let's work on some more. Okay, let's make these a little bit more confusing. E to the -x squared, holy smokes, equals e to the -4x minus 5. Now, this looks crazy, but it's not. E is just a base. It's a irrational number. Imagine pi was there. Well, I guess that doesn't really make it any easier. Okay, well, it's a base number, and it has an exponent after it. And that equals another base number with an exponent after that. And there's an equal sign between them, and both of the bases are the same. So we can use the one-to-one property here just to say that we no longer care about the e's. All we care about is -x squared equals -4x minus 5. One-to-one property. Okay, that's great. But now we have a quadratic, and the way that I'm going to solve that is I'm going to add x squared to the right side and set it equal to 0. And then I could factor or use the quadratic formula, depending on which would work best in this problem. So let me rewrite that. I will rewrite that as x squared minus 4x minus 5 equals 0. Yeah, I know. I kind of flip things over. I should have said 0 equals x squared minus 4x minus 5, but it's the same thing. I just did kind of 2 steps in one, and we're talking about logarithms, so the quadratic shouldn't be too hard. Okay, I'm looking at this, and I think I can factor this. I think this is x minus 5 and x plus 1 equals 0. All right, so multiplying that back out, x times x is x squared, x times 1 is 1x, -5 times x is -5x, -5x plus 1x is -4x, and finally -5 times 1 is -5. Everything checks out here. So now we have two things that we need to solve. So x minus 5 equals 0, and x plus 1 equals 0. So, and x minus 5 equals 0, x will equal positive 5. That's great. And x plus 1 equals 0, x will equal -1. That is also great. Since this is not a logarithm, I can have negative exponents. That's totally fine. Those are my two answers. Now, if this was a logarithm that we were solving this way, we'd have to put these numbers back in and check them just to make sure that both of them came out to be like numbers that were possible. Sometimes logarithms do not like negative numbers inside of them. So, because it was just an exponent, we don't have to worry about that now. Those are my two answers. Let's move on to the next one. Okay, 3 times 2 to the x equals 54. Now, this is actually a pretty easy question with just one extra number written in there, the 3 in front. So let's just move that over to the other side. It's being multiplied by 2x, so if you just divide both sides by 3, that should make this a little bit simpler. So 2 to the x equals 54 divided by 3, which is 18. Now I can rewrite this. The 2 to no power equals 18, like 2 to the 4th power is 16, 2 to the 5th power is 32. So this is not going to have an integer solution, but I will now use the change of base formula. So I will rewrite this as a logarithm. Log base 2 of 18 equals x, and I will use the change of base formula in order to solve it. I can use either log 18 divided by log 2 or natural log 18 divided by natural log 2. I'll use log this time. So log of 18 divided by the log of 2 equals x. And using my calculator, log of 18 divided by the log of 2. And my answer, as expected, is a decimal, 4.169925001. Okay, let's go through. Typically, we go 3 decimal places, so that would be 4.170. So x is approximately 4.170. This program does not make circles for you. I just realized that. Okay, great. Now let's do some harder ones. Okay, don't panic. Now, remember, algebra is all about isolating variables. And in this equation, we actually only have one variable. It's the x that's in the exponent right here. That's our only actual variable. So we need to get that as much by itself as possible. So I need to kind of isolate what's inside those parentheses first. And then I'll probably use a logarithm to get that exponent down to a point where I can solve it. So I have to move over the -3 and the 2, and I'm going to do them in like reverse order of operations. So anything added or subtracted, I move over first. Anything multiplied or divided, I move over next. And that should get my parentheses by themselves. So I will add 3 to both sides. So 11 plus 3 is 14. So here we have 2 times 4 to the 2x minus 3 equals 14 because I added 3. And then divide both sides by 2. We have 4, and I'll try to write it neater. 2x minus 3 equals 14 divided by 2 is 7. Okay, we have a thing here now that we can write as a logarithm. We have a base, an exponent, and then a solution. So I will rewrite this as a logarithm. Another thing to do is take a log base 4 of both sides, but we're essentially doing the same thing. So I will rewrite it as a logarithm. Log base 4 of 7 equals 2x minus 3. Now there's nothing about the left side that tells me that this is going to be an integer solution. It will be a crazy decimal. So we just have to make sure that we use enough decimal places in order for this to work. And I know I'm going to have to divide that decimal. So if I want it accurate to 3 decimal places, in the intermediary, I'm actually going to use much more than 3 decimal places. I'll probably end up using 6 decimal places. So log base 4 of 7, I'll use the change of base formula. Log of 7 divided by the log of 4. So let me see there. Log 7 divided by log 4. And I get 1.403677. That's accurate to 6 decimal places. So I'm going to use that in the meantime, and then we can start. That way, by the time we get to our final answer, 3 decimal places should still be accurate. So 1.403677. The next number is a 4, so I won't round that up at all. And that equals 2x minus 3. So for this number, I will simply just add 3 to it. And that gives me 4.403677. It doesn't affect that decimal at all, just the whole number part of it. And dividing this long decimal by 2. So let me do that. 4.403677 divided by 2. I get 2.2018 2.385. Now, I know all those digits aren't accurate, but I know the first three should be accurate. So 2.202. The next digit's an 8, so it should round up. X is approximately 2.202. And I'm going with that as my final answer. I'm even circling it, ovaling it, ellipsing it. It's one of those. I am making it rounder, roundening it, something like that. Oh, look, more awesome. Great. ln of x equals 3. Ln, when I see ln, I'm thinking e. Ln of x equals 3. What if I just raise both sides to be a power of e? That would be rewritten as e to the ln of x equals e to the third. And essentially what I'm doing here is just rewriting this as an exponential function. Well, it's not a function, an exponential equation. E to the ln, this part right here just reduces to 1, and the x comes down, it drops down, and so x equals e to the third, and e to the third is approximately 20.0855, so 0.86. That wasn't too bad. So 2.71 to the third power is approximately 20.086. That makes sense. 3 to the third power is 27, so there you go, 2.71. That's close. Okay. Now the next one, log base 3 of 3x minus 1 equals log base 3 of 2x plus 1. This is a one-to-one property problem here, and it's actually very straightforward because they both have log base 3 in them. So that means that this part right here will actually equal this part right here. This is a simpler, much simpler algebraic expression or equation. So 3x minus 1 equals 2x plus 1. It's just a equation with variables on both sides. You can subtract 2x from both sides. Okay, so x minus 1 equals 1. Add 1 to both sides, x will equal 2. That looked a lot crazier than it ended up being, which is the better way for that to go. You know, it's much better than if you start doing the problem and you realize it's much harder than you thought. Okay, wow. We got a lot going on here. We are actually going to use the properties of logarithms to help us to solve this next problem. I notice I have log base 2 of, and then a parenthesis with a bunch of stuff in it, minus log base 2 of 5. I think I can rewrite that whole side with one logarithm because they're both log base 2 and they're being subtracted. I know this is really a division problem. So this is log base 2 of 3x plus 14 over 5. And that equals log base 2 of 2x. So that might not look like it's a lot simpler, but it actually is a lot simpler because there's a log base 2 on both sides. We can now use the one-to-one property to just say, and I'll rewrite it over here, 3x plus 14 divided by 5 equals 2x. And this is not a typical looking equation, but it is just an equation. And we can solve this. There's no more weird words like log in there, and there's not even any exponents. So first I can multiply both sides by 5. You get 3x plus 14 equals 10x. 5 times 2x is 10x. And then I could subtract 3x from both sides. 14 equals 7x. Oh, so convenient. Divide both sides by 7, you get x equals 2. Wow. That looks so difficult from the beginning, and now I feel a lot of confidence, like I can solve a lot of these problems. Okay, the next problem, 5 plus 2 ln of x, 2 natural log of x, equals 6. Okay. Well, we know we want to get the x by itself because that's how algebra works, and before we can get that, we have to get ln by itself. So I have to get rid of that 5, and I have to get rid of that 2. The 5, easy enough. It's being added. I'm going to subtract it from both sides. 2 ln x equals 6 minus 5, which is 1. Now, to get rid of the 2, that's 2 times the natural log of x. I will divide both sides by 2. ln x equals 1/2. Okay. You might feel like you're a little stuck right now. You're like, well, I could do that. Now what do I do? Remember, ln is the opposite of e, so we can use the inverse function e. We can either raise both sides to be a power of e, or you can just rewrite it as an exponential function with a base e, where it's e to the 1/2 equals x. Either way, you're going to get exactly the same thing. And it's what I just said. E to the 1/2 equals x. And e to the 1/2 is a number we can find on a calculator. E to the 1 divided by 2 equals 1.6487. So x is approximately 1.649. That's not bad. Whenever you're dealing with e's or natural logs, you know that your answer is probably going to be irrational, unless something canceled somewhere in there and it makes you happy. But a lot of the time, irrational numbers come with those. Logarithms, maybe that's a little bit more. It could go either way, but whenever natural logs and e's show up, irrational numbers follow until calculus. Okay, here is the last problem for this video. So this one has to sum up everything we've done so far. It kind of does that. It combines solving equations with using properties of logarithms, and that's a wonderful thing. So let's do that. It says log of 5x plus the log of x minus 1 equals 2. Those logs don't have any bases. That means the base is 10. And there's 2 of them on the left side, and there's none on the right side. Okay, so let's just look at this on the left-hand side. Can we rewrite that with 1 logarithm? And the answer is yes. They have the same bases, 10. So they're being added, so we multiply. So it's log 5x times x minus 1 equals 2. Now, remember, if there's nothing there, it's really a 10. So I can raise both sides to be like a power of 10. This is going to be great. So that becomes a power of 10, and this becomes a power of 10. So 10 to the power of log 5x times x minus 1 equals 10 squared. All right, well, this part right here all reduces out to be 1. So that's just 5x x minus 1 equals 10 squared. Okay, 10 squared is 100. So 5x times x minus 1 equals 100. Okay, here I notice I'm probably going to have a quadratic. So I'm going to distribute 5x to the x minus 1. That becomes 5x squared minus 5x equals 100. And I just have a quadratic to solve. That's not so bad. I'm going to give myself some room by putting it over here. 5x squared minus 5x. And I will subtract 100 from both sides just to make it equal to 0. Minus 100 equals 0. Okay, factoring this. Well, I could factor a 5 out right from the beginning. Let's do that. X squared minus x minus 20 equals 0. Okay, now I don't have a leading coefficient. Everything just got easier. I'm definitely going to factor this one. So the factors of 20 that add up to -1, or the factors of -20 that add up to -1 are -5 and +4. So 5 times x plus 4, x minus 5 equals 0. And I can take each of these now and set them equal to 0. So x plus 4 equals 0, and x minus 5 equals 0. And x plus 4 equals 0 becomes -4. X minus 5 equals 0 becomes +5. Okay, so we have two solutions, but this is a logarithmic problem. And I told you before, logarithms sometimes don't like negative numbers. So we are going to have to take each of these answers and substitute them back into our problem, our original problem, to see if we get a accurate answer, especially the negative one. We really just have to check that one. So log of 5 times negative 4, just that part alone will give us an impossible domain. So that would make that thing whole not work. Remember, this is log base 10 of 5 times negative 5 times negative 4 is negative 20, is log base 10 of negative 20. And what I can't think of any exponent of 10 that will give me negative 20 as a solution. So that's tough right there. You can't really take a logarithm of a negative number there. So the negative 4, actually, this one is not a real solution. The 5, however, the 5 works totally fine. Yeah, it will be the log of 25, which has a decimal. And it will be the log of 5 minus 1, which is 4. The log of 4 has a decimal answer. Add them together, they equal 2. Totally fine. Okay, so our only real solution is the 5 here, because when we tried to put the negative 4 back in, we got a domain error with this first part right here. We would also get it here because this would be the log of negative 5, and that would also have a domain error. You can have two impossible terms being added together to give you a positive 2. That didn't work. So the solution to this one was exclusively 5. Everybody breathe. You made it. You made it all the way to the end of this video. Nice work. I'm proud of you. So thank you for making it to the end of this video. I hope this helped you learn a little bit about solving logarithms. At least it gave you some examples that you can use when you're doing all of your logarithms in your personal time, maybe when you're just doing your morning math reflections before you actually go to school, when you just think about math the entire morning. That's great. You can do that. And if you make it this long, maybe leave a comment like about morning math reflections and how you use them to help you really get through the day. I think that would be wonderful. And I mean, you probably should just move on to actually trying to solve some more logarithmic equations or expanding or condensing logarithmic expressions. Maybe at this point you should try to do that. But if you just want to sit here and reflect a little bit about how wonderful this whole experience has been for all of us, that's wonderful too, and I appreciate that. So thank you for making it this long, and I will see you on the next video. Good luck.